we this is EE6403 Transducers course, lecture 11, right? So let's recap what we have learned so far. So we learnt about strain gauges, the strain gauges are transducers that we use to measure strain, and though there are different types of strain gauges that have been developed, the one strain gauge that is very popular. In fact, today if you go to a market and buy a strain gauge, 99% of the time it would be a resistive film type strain gauge. And also again, there are different types we learned in the last class. Bonded type, right, only you will get. Now if we look at the strain gauge, we on a insulating material, a film of resistive material is coated in this fashion most of the time, and this will be the axis of the strain, and this is known as the cross axis or quadrature axis of the strain. And if you want to measure strain, then you have to mount the strain gauge so that its axis of sensitivity is in line with the strain that you are trying to measure. And we already knew that if there is an angle between the actual measuring strain and the axis, then what you would measure is Em cos theta. If you do not know the axis of the strain, then you can use what are known as rosettes. Rosettes are multiple strain gauges. The two-axis rosette, there is one x-axis sensitive, the other one is y-axis sensitive. Right? Or you can also use three axis rosettes, 120 degrees each, 120 degrees right, and we put a strain gauge in this fashion. These are tailor-made. The manufacturer makes them for you and put exactly 90 degrees or 120 degrees and gives you as a single integrated piece. And in the last class we started looking at how to get an output from a single active strain gauge. So we have an amplifier here, right? In the yesteryears, we used to use AC excitation, and the output will be an amplitude modulated signal. So you need to demodulate and get the E0. So such thing is called carrier frequency amplifier. This amplifier then becomes normally carrier frequency amplifier encompasses the demodulator also. The carrier frequency amplifiers are quite popular 30-40 years ago. Many leading manufacturers like HBM, Hewlett Packard, they all used to make carrier frequency amplifier and make a lot of money. Today, of course, we don't need AC excitation. We can use DC excitation and put a DC amplifier, right? So, thanks to the invention of an op amp, right? Uh, we have the op amp here, non-inverting input, inverting input, and output, right? And last class we saw that if I connect two resistors here and ground this, I get if I give EI, E0, if this is R2, this is R1, would be minus R2 by R1 into EI. It is also possible to get non-inverting. If I give EI here, I connect this to ground, R1, R2. In this case, E0 is equal to 1 plus R2 by R1 into EI. Now we also saw another circuit. Right. So R1, R2, R2, R1. Oh, sorry, this is R2, this is R1. This is E1, E2. This is called the difference amplifier. This is R2 by R1 into E2 minus E1. The problem is if I put an E1 here, there would be a current that would be drawn from E1. E2 also, there will be a current drawn from E2. So that means this amplifier has an input resistance, and if I connect it to the bridge output, then that input resistance comes in parallel with the resistance of that particular input, so it's not good. So we call this as difference amplifier. The solution here is to use what is known as an instrumentation. Amplifier. There are several different configurations, but one configuration that is really popular is the 3 op amp configuration. So I have plus, minus here. There is a resistance in the feedback. Minus, plus, and the resistance in the feedback. We put a difference amplifier here. So this is this is a very popular. We call this as gain determining resistor called RG. This is not a gauge resistance. Let me put it as not RG, amplification factor RA. So these are all R. Okay. So if I call this is E1, this is E2. I call this output EA. This is EB. Then this we already seen. So E0 would be equal to EB minus EA. Right. Now let us look at what is EA. If I have E1, this is an op amp, so this will be E1. Again, if I put E2, this will be E2. Whatever is the voltage at the non-inverting terminal will appear across the inverting terminal if the op amp is working properly. Similarly, here whatever is appearing here will appear here. So this is E1. So this current E1 minus E2 by RA, right? And the same current where this current is 0, input to non-inverting input or inverting input takes 0 current in an op-amp. So this current has to come here and come here. So there will be a voltage drop here. There will be a voltage drop here, plus minus in this direction. So this voltage drop, let me write it here. This voltage drop would be I is E1 minus E2 by RA. The resistance is R. Right? So this also is the same, because the same current is flowing in this direction. Only the polarity will be plus here and minus here. Okay. So now with this I can write EA. This is E1 plus the drop in the resistor R would be E1 minus E2 divided by RA into R. So that's the EA. EB would be E2 minus, because we are going from plus to minus on this R in this direction, E1 minus E2 by RA into R. Now I can write E0 is equal to EB minus EA, E2 minus E1 minus E2 by RA into R minus E1 minus E1 minus E2 by RA into R. Right? So let me take this minus inside. So this is E2 and this is minus E1. If I take this minus inside, I will get plus. It was E1 minus E2, that will become E2 minus E1 by RA into R. Again I take this minus inside, this becomes plus E2 minus E1 by RA into R. So if I take E2 minus E1, this is 1 plus, there is R by RA, so this will be 2R by RA. So the output will be the difference voltage E2 minus E1 multiplied by a gain which is given by 1 plus 2R by RA. So this is the instrumentation amplifier. Normally if I use a difference amplifier, the another problem is difference amplifiers do not possess a good common mode rejection ratio. The common mode rejection ratio is given by 20 log AD by AC, where AD is the common mode gain, AC is the common mode gain, AD is the differential mode gain. All of you would have learned this. Otherwise, you can go back to any book on op amps or linear integrated circuits and refresh. So this instrumentation amplifier is very popular. Today you don't have to make them with op amps. They are available where the gain is set by one resistor. So this is gain setting resistor. Right? For example, AD 620, AD 720, INA 101. There are several manufacturers, several numbers with differing characteristics. You can buy them today. They are not that highly expensive as it was a few years ago. So the basic thing is, if I have a bridge say this is R naught into 1 plus delta, this is R naught, this is R naught, this is R naught. I take the output instrumentation amplifier. Please remember, this is not an op amp. This is instrumentation amplifier with a gain A, and I excite it with a battery EB. So I call this as output of the bridge, E0 of the bridge. We have already derived last class. E0 of bridge is EB by 4 into delta by 1 plus delta by 2. So final E0 would be A times EB by 4 into delta by 1 plus delta by 2. Right? So the output is still will possess some nonlinearity if delta is small. Please remember what is delta for us. Delta is gauge factor into epsilon. Right? The epsilon is the strain that is put on the strain gauge, and gauge factor is the gauge factor of the strain gauge. Okay. So we can put an amplifier here, but the linearity, the output will still be non-linear. Is it possible to get a linear output for single active strain gauge? Right? So one way is to use what is known as a current mirror. Right? Right? This is I, this is also I, and this is R naught. This is R naught into 1 plus delta. So I take these two outputs, put an instrumentation amplifier. So output would be E would be A times, where A is the gain, I R naught into delta. Right? This is not very popular, even though it's simple. If you want to realize this, you need what is known as a current mirror, two current sources of exact same value, and also a dummy resistor R naught. But if you are making an IC, this is a very popular circuit. So if you are buying a strain gauge IC, single conditioning IC, 99% of the time you can be sure that they use a current mirror, because getting a current mirror in integrated circuit form is quite easy. The other method is to use a single op amp. This is E0, and I, as usual, put EB. So analysis, you can easily do the analysis. So this is R0, R0, this is R0, this is R0 into 1 plus delta, right? That's a strain gauge. So if this is EB, this is R0, R0, so this point will be EB by 2. So this point will also be EB by 2. Please remember, whatever is the potential at the non-inverting terminal will also appear on the inverting terminal. So one terminal of R0 is at EB, another is EB by 2. So there will be a current here. So this current will be EB by 2 R0. Right? So that current, because this current is 0, the inverting input doesn't take any current, so the same current has to flow here. So this current is also EB by 2 R0. So there will be a drop here. So this drop will be EB by 2 into 1 plus delta. R0 will cancel out. So I will get this voltage. So this voltage is there. So E0 is equal to EB by 2. This voltage I am going from plus to minus. So that has to be minus EB by 2 into 1 plus delta. Right. So now I can write E0 is equal to EB by 2 minus EB by 2 in plus EB minus again, not minus EB by 2 into delta. I just expanded this. So plus EB by 2 minus EB by 2 will cancel. So I will get E0 is equal to minus EB by 2 into delta. The linearizing circuit is simply called a single op-amp, single active strain gauge linearizing circuit. So let me write this here: single op-amp, single active strain gauge linearizing circuit. But here if you see the output is directly proportional to delta, and delta is normally very small, 10 power 4 or minus 4, 10 power minus 5, in that range. So the output that you will get will be very small. So normally what we do is we take this output and put an inverting amplifier. Okay. So I put R2, R1, and I put E01. E01 is equal to minus R2 by R1 into E0. That would be R2 by R1 EB by 2 into delta. So I can now make R2 by R1 100, 200, whatever gain I want, I can put. So whenever we use a single op-amp linearizing setup, we need to amplify the output. There is one more linearizing circuit, very quite popular. That is given here. Again, we have the bridge R0 into 1 plus delta. This is R0, this is R0, this is R0. We take the output to an instrumentation amplifier, right, with gain A. This is not an op-amp. This is instrumentation amplifier. I will put as IA here, and the output is E0. What we do is we take a part of E0. Right, let me say that's grounded. This is R1, this is R2, part of E0, and we take a summer. Right? It's simply, if there are two voltages, it gives the addition of the two voltages, and that is feedback. So let me assume that this is bridge excitation voltage. Right? Please remember, bridge excitation voltage now is combined with the part of E0, and so I call this as E excitation. So I can write E excitation equal to, if this is E0, this is beta times E0, where beta is equal to R2 by R1 plus R2. Get less than 1. Beta is always less than 1, right? So I have E excitation is E bridge plus beta E0. So that's the output here. Okay. Now let us look at this. This is E0 bridge. So E0 bridge, we already know, is E excitation divided by 4 into delta by 1 plus delta by 2. Right. Now I can write E0 is equal to A times E naught bridge. Please remember, all we are doing is we take the E excitation and then we amplify it using the instrumentation amplifier. So E naught is amplification A times the output of the bridge. So I have A times E naught bridge, that would be A times EE by 4 into delta by 1 plus delta by 2. Now I already know EE, substitute EE. What is EE? EB plus beta E naught. This is beta E naught. So A into EB plus beta E naught by 4 into delta by 1 plus delta by 2. So I can expand this. This is AEB by 4 into delta by 1 plus delta by 2 plus A beta E naught by 4 into delta by 1 plus delta by 2. That is E naught. Okay. So I take this E naught to the other side, right? I take it to this side. So this will be E naught minus A beta E naught into delta by 1 plus by 4 into 1 plus delta by 2. This is equal to A E B delta by 4 into 1 plus delta by 2, right? So I take E naught out here, E naught into 1 minus A beta delta divided by 4 into 1 plus delta by 2, and this doesn't change, AEB delta by 4 into 1 plus delta by 2. Now I take common 4 into 1 plus delta by 2, this is E naught, and here 4 minus 2 delta, right? If I take this inside, minus AB delta, right? 4 plus 2 delta minus AB delta. This is 1 plus delta by 2 into 4 is 4 plus 2 delta. So that goes to the numerator, is equal to AEB delta by 4 into 1 plus delta by 2. Now I can cancel 4 here. So I will get E naught into 4 plus 2 delta minus AB delta is equal to AEB delta, right? So I can write here E naught is equal to AEB into delta divided by 4 plus, if I take delta here, this is 2 minus A beta, right? Please remember, beta is what we set, R2 by R1 plus R2. A is also we set. Now, if we make A beta equal to 2, right? So this will become 2 minus 2 will go to 0. It will go to 0 if A beta equal to 2, right? So if I make A beta equal to 2, then I am going to get E naught is equal to AEB by 4 into delta. So my output is only the excitation voltage EB, and amplified also by amplification factor of A by 4. So this is a very linear amplifier, linear output amplifier, because if we look at the circuit, what do we do in the circuit? We take a portion of E0 and feed it back to the bridge. So because of this, this is known as feedback compensated linearizing circuit, right? It is quite popular in terms of single active strain gauge. And of course, if I have this is all these things are called quarter bridge, because only one of the four bridge resistors is an active strain gauge. So we call this as quarter bridge circuit. Uh, then we also learned that we can have half a bridge and a full bridge. Both are linear, uh, inherently linear output. So you don't have to linearize them. And we also see that if I put half a bridge with two active strain gauges, I get double the voltage, EB by 2 into delta. And if I put full bridge, I will get EB into delta, 4 times the output along with linearity. Okay. Uh, Now, if we look at the uh, strain gauges, you can use the strain gauges to straight away measure strain on any particular structure that you would like to measure strain. Uh, it is also possible to use strain gauges as sensing for load or force. So these are popularly called uh, road cell, right? And the uh, there are different types of load cell. One is called the cantilever type load cell, where we put a cantilever let me just remove this. And if we put a force or a weight, this is fixed like a wall, and again I am going to exaggerate, this may bend like this, right? Normally we don't allow so much of bending, otherwise the cantilever will break. It will be very small bend, uh, just to show you that what happens if it bends. So here if I look at, this is epsilon, right? Here the it's minus epsilon. This is expansion, this is contraction. So expansion strain, I call it as plus epsilon, and when it is trying to push contract, I'm calling it as minus epsilon. So now we can put one strain gauge here in this axis. This will take sense plus epsilon, and if I put at the bottom a strain gauge, that will put minus epsilon. So we can actually put two strain gauges at the top and two strain gauges at the bottom, and we can make a full bridge and excite it with a bridge supply, uh, put it through an instrumentation amplifier. We get E0, which will be proportional to the force applied or weight applied. Uh, so the cantilever is one type. Many times what we do is we use the uh, cantilever in right, we put here, and put the force at the center, so it will try to buckle like this. So we can put 4 strain gauges on the 4 sides, on both sides. So we call this as a double beam or double cantilever load cell, very popular for measuring weights. In fact, if you buy a weighing machine today, you can buy a load strain gauge based weighing machine for a few hundred rupees, that to a digital one. And if you open up, you would see that there is a load cell, something like this. Let me draw it here. So you take a elongated, right, and then you put slit here like this. So this through and through material is removed, and you put a weight here. So we will get plus epsilon here, minus epsilon here, minus epsilon here. So again, we put 4 strain gauges and connect it in a bridge form. The output will be proportional to the weight. Again, when you come to laboratory, we will show you the actual load cell, and also we'll see the actual weighing machine. We'll make a lot of measurements on that. There is an experiment with the load cell that is attached to a weighing machine. Okay, so this is cantilever type. There is also another type called button type, or it is sometimes the button type is also called mushroom, because the shape is like a button or a mushroom. So we have a hemisphere placed on a circular plate, right, and this circular plate is connected with a rod of square dimensions, and again that is put on a circular plate, right. So you apply the force on top, you put the strain gauges on all the 4 sides, and you can either have a single bridge or a double bridge, because if I put 8 strain gauges, I can make 2 bridges of 4 each, connect them in parallel, connect them in series, whatever I want I can do. So sometimes you also use a double bridge load cell. So this is the force. Again, I am going to expand this. If this is my square, right, and if I apply a force, this may bulge like this. This may bulge like this, right? Just imagine that you are compressing a square, the middle portion will expand so that the height becomes smaller. So you have both the plus side. So if I look at this, this is expansion and this is contraction, right? So if I look at on this scale, it will be something like this, right? So here it's contraction, here it is expansion. So we can get both plus epsilon and minus epsilon. So this kind of load cell is again quite popular. There is a third type of load cell called ring type load cell. Right? In a ring type load cell, as the name indicates, you have a ring which is subtended by 2, right? So this is normally hung from ceiling, or you can even permanently fix it with a bolt and nut and apply a force here, or ulta, you can keep it on the surface and put an apply on the force. So once again, I am if the force is like this, I am exaggerating. Oh. So this may become oblong like this, right? So once again, you have on the outer side there would be uh, expansion or plus strain. On the inside there will be a minus sign, so I can fix one strain gauge here, another strain gauge input, another strain gauge here, another strain gauge here. So I'll get 4. 2 are positive, 2 will be sensing the strain produced by this force on the ring, which will be positive, and the other one will be diametrically opposite or negative. So once again, you get a full bridge configuration here. So we can put all our strain gauges. So the this type of load cells are also quite popular. The one thing that we should be careful is, if I look at the gauge resistance is R0 into 1 plus gauge factor into epsilon. Now any resistance R will have R0 into 1 plus alpha theta plus beta theta square plus gamma theta cube, where theta equal to temperature. So we call this as temperature coefficients of resistor. For most metals, beta and gamma are not very high. They will be small. For example, alpha for copper is about 10 power minus 4, 4 into 10 power minus 4. But if that is there, then my gauge resistance will be R0 into 1 plus alpha theta. I am assuming beta and gamma are small, into 1 plus gauge factor into epsilon. So as theta varies, my R0 is also going to vary. So I should ensure that I have an output which is independent of R0. In that, half bridge and full bridge, half bridge and full bridge gives automatic temperature compensation. Right? On the other hand, if I have a quarter bridge, I must take care that the temperature doesn't change or provide temperature compensation. How do I give compensation? I put here. So this is my R0 into 1 plus delta. This I put R0. This also R0. This also R0. This, instead of putting a resistor, I put a dummy gauge and expose the dummy gauge to the same temperature as the strain gauge, right? In such a case, I will get the two resistors, right? The effect, temperature effect on this R0 will be compensated by the temperature effect of this R0. Apart from load cell, strain gauges are also used. strain gauge pressure sensor. Right. Suppose I put a diaphragm and I put P1 and P2. I make P2 greater than P1, and I take a cross section here. So this is fixed here, this is fixed here. So this is the diaphragm, right? Thin sheet, and if P1 and P2 greater than P1, again I am exaggerating, the diaphragm will bend like this, right? At these two ends, the displacement will be 0. At the front end, the displacement will be high, depending upon the flexibility of the diagram. You have semicircular expansion, or you have sine wave expansion, right? One of them doesn't matter. Again, we can fix strain gauges here and measure the strain on the diaphragm, and that would give me uh, an output proportional to the differential pressure, right? P1 and P2. We will revisit this when we talk about pressure sensors. At that time, I will talk about all types of pressure sensors. At that time, I will talk about the strain gauge diaphragm type of pressure sensor. So we have learnt about the strain gauge as a sensor. It's a resistive sensor which senses the strain, right? And I also told you that today when you say strain gauge, you simply mean that it is a bonded film type strain gauge, and the metal film that they use a resistive alloy metal that has very low temperature coefficient, right? And we can use strain gauge principle by for pressure measurements, for load measurements. We can also use it for acceleration measurement, right? We will see that when we talk about micro electro mechanical systems. And so I stop here. We will continue in the next class with more resistive type sensors. So